Oh, wrong way. There we go. That's good. Okay. So which homework problem are we asking about?
I think it's 3. Homework 5.
Problem 3 on homework 5, right? So we wanted to see a problem. Someone can take the nice chair too. I'm not going to be using it anymore. We wanted to look at a problem that was a weak base.
Yeah, a strong acid.
Titrate. Strong acid. So problem 3 on homework 5 has one of those. What's the weak base we're dealing with in that case?
10 milliliters of 0.1 molar methylamine.
Methylamine is a CH3NH2, which has a Kb associated with it of. We have to look.
I wrote it down earlier. 4.4 times 10 to the minus 4.
We can also turn that into a Ka if we wanted to.
2.27 times 10 to the negative 11.
And we're titrating with a strong acid. Identity of the strong acid doesn't really matter, but what concentration?
0.1.
Oh, that's nice. Right, this makes it easy, right? When the analyte and the titrant have the same concentration, that makes things really easy. It's 10 milliliters to the equivalence point, 5 milliliters to the midpoint, done. Right? Because it's the same volume, same concentrations. Molarities will cancel out. Okay, so let's pick a problem along the curve.
Let's do like 7.
And that is
7 milliliters of the strong acid.
D?
Yeah.
So this is homework 5, problem 3, part D.
Yeah.
7 milliliters added. Now, there's a couple things that are going to make this easier for us to logically think about. First off, we can think about where we are. I almost always start by just doing a rough titration curve. Think about where I am on the curve. Now, this is a weak base titration curve, so it's going to look like this. I know it's 5 milliliters to there. I know it's 10 milliliters to there. I know that this pH is going to be something like 10.8 if I can do logs in my head. And I know the pH here should be lower than 7. That one I can't do in my head. That one we'd have to calculate. When I look at doing 7 milliliters, I'm going to be someplace over there, right? I shouldn't be at the big drop yet. I should still be somewhere in the buffer range. If I'm in the buffer range, you notice this is all just logical thinking about the problem, not actually doing any math. If I'm somewhere in the buffer range, what equation am I going to use? Henderson-Hasselbalch. So I'm going to set this up where I'm going to have pH equals pKa plus log conjugate base over weak acid. Now I know what you're thinking. You're thinking, whoa, isn't this a weak base? Don't I need to be doing something different? Remember, when we're in the buffer range, we can also look at methylamine as if it's donating a proton, or we can look at the methylamine as if it's accepting a proton, or we can look at the protonated version as if it's donating a proton. Like, as long as we're in the buffer range, we can consider the acidic behavior or the basic behavior. We can go, because it's an equilibrium, we can go either direction. So it's almost always easier to consider the acidic behavior. So we're looking essentially at the equilibrium of CH3 NH3 plus going to CH3 NH2 plus H3O plus. Right? When we're going backwards like that, this is kind of backwards, but this makes it so we're talking about H3O plus. We're talking about a weak acid, and we can treat this just like everything we did with our regular Henderson-Hasselbalch equation. Everyone scoot in a bit more. Don't make Ethan sit in the hallway.
You can come in.
There's
The
nice chairs available. Ethan likes hiding in the hallway, but everyone scoot in a bit more. And Dr. Rice's chair is also available. So we've got our logical start. We have a rough idea of where the pH should be. So if we get something totally wrong, we should be able to tell pretty quickly.
So do we start off by pretending that this already has accepted a proton, and then
Well, now we can go through
that's
our logic, right? So remember, this takes care of equilibrium, right? This thing does our equilibrium for us, right? We still need to do the stoichiometry to figure out what we plug in for our conjugate base and weak acid. So let's do the stoichiometry to get to this idea. We're going to be starting with our CH3 NH2 plus H3O plus, right? This H3O plus is from the strong acid. I don't care what strong acid, as long as it's a monoprotic strong acid. If I give you a diprotic strong acid, that would be mean. Let's use a monoprotic strong acid. This is where we're going to form the CH3 NH3 plus water that I don't really care about. I know how many milliliters I have here. I've got 10 times 0.1. That's going to give me 0.1 millimoles. And then I've got 7 times 0.1. That's going to give me 0.07. Oh, wait, sorry. Math is hard. Dividing in my head doesn't work. That's 1 millimole. And then I'm going to have 7 times 0.1. That's going to give me 0.7 millimoles. I'm going to start with 0 here, and I don't care about the water. My reaction step, I'm going to subtract my limiting reactant, which in this case is the strong acid, minus 0.7, minus 0.7, plus 0.7. I'm going to look at what I have left over afterwards, my excess. I'm going to have 0.3, 0, and 7. Sorry, 0.7. Now at this point, I say, okay, this is my acid compound. This is my base compound. I can go ahead and just plug right into this. My acid, 0.7. I can plug in my base of 0.3.
Oh, so it's like doing it in reverse.
Mm-hmm. Because the equilibrium we're looking at is going that direction. But keep in mind, it's an equilibrium. It's always double arrows, right? So I'm looking at this thing going in reverse, essentially. Notice right here I put in my millimoles. That's okay, because if I did 0.3 divided by 17 divided by 0.7 divided by 17, the 17s cancel out, right? Total volume is the same. Total volume cancels out. I can plug in my pKa, which I think, actually, can someone calculate what the actual pKa is? I did it in my head. Calculators out. YouTube. I was almost right doing stuff in my head, but so we can plug that in. Notice the reason, again, just to be clear, the reason I get to pick whether I'm looking at the acidic behavior or the basic behavior is because I have weak acid present and I have conjugate base present. So I get to think about this either as the weak acid interacting with water or the conjugate base interacting with water. It's almost always easier to think about the weak acid interacting with water because then we get H3O plus as our product, which means we're already solving for pH without having to do any extra steps. Okay, then you solve. We could do the same thing for every point on the curve, right? So if we wanted to do 2 milliliters, we're going to change this 0.7 to 0.2. If we wanted to do 5 milliliters, we change this 0.7 to 0.5. If we wanted to do 12 milliliters, 14 milliliters would mess it up. Why would 14 milliliters mess it up? Let's finish calculating this. Let's get a pH, and then we'll look at 14 milliliters.
10.27 for this pH.
pH 10.27. Is that a good answer? So less than 10.8, which we expect going along this curve, and is before the big drop. We're still in the buffer range, which we expect. Looks great. Looks good. What happens when we go to 14 milliliters? That is to say, we go to part G.
You're going to have more. It's going to be out here. Right.
Where on the curve would you go to? If you had 14 milliliters, which is part G, so if you had 14 milliliters, you'd essentially be somewhere down here. You'd be past the equivalence point. And if we look at this, if we have 14 times 0.1, I'm going to have 1.4 here and 1 here. Past the equivalence point, my acid becomes the excess reactant, and my weak base becomes the limiting reactant, which makes sense because the equivalence point is where I've used up all of my weak base. That means when I go ahead and subtract my limiting reactant is now the weak base. I end up with 0 weak base left over. I end up with 0.4 millimoles of my weak acid left over, and I make this conjugate acid over there. Now, we could go through the trouble of setting up an ice table. In this case, we have to look at it as the conjugate acid interacting with water because there's no base left. So I have to do it in terms of conjugate acid. No choice. And I can look at this and I can say, okay, I could go through the whole trouble of doing the ice table. But if I'm going to be doing like a plus x, and a minus x, if I use the x's small approximation, I just get 0.4 for my concentration of H3O plus, for my moles of H3O plus again. Right? The amount of dissociation from that weak acid isn't going to matter if x is small is valid. So just like we saw with our weak acid strong base, past the equivalence point, the pH is completely determined by the excess titrant. I'll say that again. Past the equivalence point, the pH is completely determined by the excess titrant. Don't need to worry about equilibriums at all.
So we're just doing the concentration.
0.4 divided by total volume, which is going to be 24 to get molarity. Take the negative log of that.
Okay.
And you're good. What other questions do we got?
I have one question about lab.
Sure.
I'm confused on the for the chloride test 2.1. It says to.
Really? The chloride test is so straightforward. I'm kidding. It's not. It's not.
I was like, because the reactions that would occur between nitric acid and any carbonate ions in solution, but then it says that they'll have a special reaction.
Oh, so nitric acid plus carbonate would go to since nitric acid is strong, it'll actually do this twice. To form H2CO3. This decomposes H2O plus CO2. So the carbonate reaction. That's something we should remember from Chem 127 and from the second week of class when we did the carbonates test.
And then do we do that with each ion, or like each equivalent?
Well, this really only happens with carbonate, right? So
the whole point, and the reason we have you do that is, what's the point of adding nitric acid?
It gets rid of all of the carbonate,
Why do we want to get rid of the carbonate?
so that way you can determine what's actually in there.
So it turns out, if you had Ag plus, and you had CO3 2 minus, and you had Cl minus, you'd end up with a competitive precipitation. So we get rid of the carbonate so that way we can form more, like it doesn't mess with our other expected precipitations.
Okay.
Could you use any strong acid?
Yeah.
Okay.
Yeah. We don't use hydrochloric acid though
Because that's what you're looking for.
chlorine, right? Same issue I think with sulfuric acid, right? You can have silver sulfate.
Okay.
I'm trying to think of the perchloric acids I think would be okay. But yeah, so you have to think about like nitric acid is safe because silver nitrate is soluble, right?
Oh,
So it's
yeah.
not going to interfere with any of our precipitations. And that's why we use nitric acid. Which is funny because next week, nitric acid ruins everything. So we have to use a different special acid. Question.
So if we're finding the value of the titrant we need to get a page past the first equivalence point, do we just add like the volume of the first equivalence point after we do all of that?
Yes, you're talking about a polyprotic acid. Do you have an example you want to?
I was looking at the one from yesterday where you wanted to find what volume of titrant we need to reach page 6.2.
And this was for, what was the problem? Just, we'll do it right now because I'm sure other people want to see that as well. You want to see that? You want to see?
Yeah.
For 30 mils of 0.1 molar.
Sorry, what was that?
For 30 mils of 0.1 molar malonic acid, a polyprotic acid would K1 times 10 to the negative third, and K2 2.0 times 10 to the negative 6, with 1 molar.
That was 2.0.
2.0 times 10 to the negative 6, with 1 molar NaOH.
1 molar?
Yeah. Oh, 0.1 molar.
I was like, that's going to be a fast titration. So again, let's go ahead and think about the logic of what we have to do here. We can make a curve. We got 2 lumps. Ka1 is going to be like 2.6, 2.5 maybe, right there. Ka2 is going to be like 5.9.
It was 7 yesterday. I don't really know.
What's that? Am I doing this wrong? Oh, you're totally right. It is 7.
Wait, is this your Ka2 right here?
Yeah.
Okay.
I was trying to write fast, and so I got a little sloppy. I can't do that one in my head all of a sudden.
It is 5.7.
5.7. Okay, no, I can do it in my head. Totally had me down. Oh, I don't know. So we have some information. We can also do the volumes real quick. 30 to the first equivalence point, 60 to the second equivalence point. We can also think about the 2 reactions that are going to happen. I'm just going to be generic here. I'm going to do H2A goes to H3O plus HA minus, and HA minus goes to H3O plus A2 minus. Those are the 2 reactions that we'd be dealing with. And we say, okay, to a pH of 6.2, that's going to be past the second midpoint, which would be at 45. So we're expecting an answer between 45 and 60. Notice if this is a multiple choice question, just look for things between 45 and 60. Now, you probably know that, and it'll have 3 answers between 45 and 60 and 1 answer out, so you can at least eliminate one of them as a bad choice. But we can logic through it and kind of get an idea. We can also look at this and say, okay, let's see if we can be even more. Do you expect it to be closer to 45 or closer to 60? Is 6.2 close to the midpoint or kind of far from the midpoint? Like, so keep in mind, this goes from 5.7, this should go up to 6.7. Kind of like right halfway, right? So maybe it should be something like 50, 52. Again, just a little bit of logic. Let's get the actual answer here. So when we set this up, we're in a buffer region, so we can use the Henderson-Hasselbalch equation. We can say pH equals pKa plus log conjugate base over weak acid. And when we look at this, we're going to be looking at the second equilibrium, right? The first equilibrium happens down at 2.6. We're going to be looking up at 6.2. But when I start thinking about my stoichiometry, since I'm doing it in 2 steps, if I'm just looking at the number of moles for my stoichiometry, if I'm just looking at the stoichiometry past the second equivalence point, I'd be looking at HA minus plus OH minus goes to A2 minus plus H2O, right? I'm looking at the stoichiometry just past the second equivalence point. The Henderson-Hasselbalch takes care of my equilibrium. I'm looking at the conjugate base of weak acid I plug in. My HA minus, after the second equivalence point, that means all of my H2A has all become HA. So I know that the moles I started with for H2A all becomes HA. So that's still going to be 30 times 0.1.
Wait, so that's at the second equivalence point or the first one?
First equivalence point.
Oh,
First
okay.
equivalence point is all this reaction. Second equivalence point is all that reaction. So after the first equivalence point, I should have all HA plus whatever else I did to it, right? And what we're looking at here, because of the way we're parsing this question, we're really looking at we're essentially saying, okay, let's pretend we start here, and then it just looks like a normal titration curve, right? If we ignore that first equivalence, we can just treat this like a normal titration, but then we'll be off by 30 milliliters. But the math is much easier if we just do it like we've always done it. So let's do it like we've always done it, and then realize we're off by 30 milliliters. So we'll do it like we've always done it. I'm going to have some volume times 0.1. I don't know what volume that is, 0. I'm going to have, we don't even do it this way. Let's do it the right way, right? We can do it this way. This is fine. We're going to have minus V times 0.1. We're going to have minus V times 0.1. We're going to have plus V times 0.1. We're going to end up with 30 minus V. I'm just going to do some factoring because the concentrations are the same, makes life a little bit easier. I get 0, and I get V times 0.1. I'm going to plug this in for my conjugate base. I'm going to plug this in for my weak acid. So I'm going to get 6.2 equals, is 5.7 the right number, or is it 5.7 something?
5.69.
5.69 plus log V times 0.1 divided by 30 minus V times 0.1. Look at how nice it is when the concentrations are the same. This is, I will admit, this is the #1 problem with examples, especially in textbooks. They always give you these simple things, and they're like, oh, then you just erase the concentrations. And then, like, none of the other problems let you do that, right? The concentrations cancel out, and then no other problems do that. Let's leave those concentrations there, just because chances are on an exam, I'll give you different concentrations. So at this point, we've got one equation, we've got one unknown, we just solve. Calculator's out, let's go ahead and solve this. Everyone's good to know, there's chairs all the way, there's a nice chair. I really can't do this in my head, so I really need your help. Calculators, calculating. I don't even think I can do 6 minus 5 in my head right now. 6.2 minus 5.69. 0.1, 0.51? 0.58. Yeah, see, can't do it.
I got one.
We're
I put a 2 and
Oh. I can do that in my head, it turns out. What's 10 to the 0.51? Is it like
3.24.
Mm. So I just did a bunch of algebra. For those of you watching at home, I just did a bunch of algebra. I did 30 minus v times 3.24, add 3.24 v over. That gives us 4.24 v. Divide by v, 3.24 times 30 divided by 4.24. I think I did my algebra right. What number did you all get?
29.69.
I tried that.
Does that make sense? This should be a little bit less than 30. Yeah, that makes sense. Great. So, 29.69. Ooh, 29.69?
I got 22.
I got 22. Yeah, I got 22.
That's more what I was expecting.
And then I
Um,
did that.
You made a V disappear. There should be a V on
Oh,
top
whoops,
there.
yeah.
Which is going to make your 3.24 a 4.24, which is why you ended up with something a little bit larger than expected. 22.9. Okay, now, that was pretending like we were just doing this. We know that's going to be off because we already see the answer has to be between 45 and 60. So when we look at this, we say, okay, we can't actually ignore the entire first proton. We have to add in that original 30. But notice the math doing it this way, where we're just pretending like we're doing a single proton problem, is just like everything else we've been doing. We just have to remember to add that 30 back in. So then this 22.9 is going to become so we add the 30 back in because it's the second buffer. That's going to give us 52.9. Whoa. What was our estimate from before? 52. We said like halfway between 45 and 60, which was like 52. So on multiple choice questions, you should actually do the work instead of just like estimating or guessing. But if you're like, wow, I don't know how to do all this math, or if you're like, wow, this test is really long for 50 minutes, like if you can estimate and guess, like that's a valuable skill. Being able to look at something and be like, I'm going to ballpark this without actually doing the calculation, like that's a really valuable skill. The only thing that's dangerous about that is if you're like, I'm going to ballpark this and guess without doing the calculation, and you just have no frame of reference, like how heavy is the Earth?
Yeah.
I don't have a frame of reference for that. There's probably some, what was the this is a fun one. How long does it take to fly around the world? I don't know. If I think about how long it takes to fly from like LA to New York, that gives me like something. And then like you just like, how many flights from LA to New York does it take to get around the world? It's like, what is that, like a 4-hour flight?
Isn't it way more than that?
Yeah.
Is it a 6-hour flight?
Yeah, something like that.
Okay. I haven't flown in a while. I keep flying across the Pacific instead of across the country, so I've lost track.
So
So
can you do the same thing for strong acid, weak base, where you estimate it?
Yeah.
Okay.
Yeah,
And
you can do the
you
exact same
just
thing
add
with
the volume
strong acid,
in.
weak base. Yep.
Okay.
Yep. All of that, pretty much everything we've done with weak acid, strong base also works for weak base, strong acid.
Okay. All right. Awesome.
Cool.
Thank you.
See ya.
We tried solving a first equivalence point for a diprotic acid.
What do you mean solving the first equivalence point?
Like the volume
Oh,
base needed to get the first one.
volume to the first equivalence point
Yeah.
for a polyprotic? Yes. I was worried you meant the pH, and I was like, I'm not going to do the whole like hour-long calculation thing. But
Oh, yeah.
volume, let's go ahead. I just wrote it's 30. How did I know it was 30? What's the volume to react to the first proton? So let's think about this.
Oh, yeah.
You got it?
Yeah.
Yeah, so it turns out that it's the same logic we've always had, right? We have the volume to the first equivalence point is still going to be equal moles of base to weak acid we have. So it's still going to be 30 times 0.1 gives us the number of moles. I want that equal to the number of moles of base. That's going to be volume times 0.1. In this fun example, the 0.1 cancels out and you get 30 milliliters.
So the volume is like the same as everything we've always done, but the pH is the pKa1 plus pKa2 divided by
Yes, right. So the reason I paused when you said, can we do a first equivalence point calculation, is because to actually calculate the pH here is not trivial, right? It takes quite a bit of work because you have to look at how these two equilibria compete with each other. How well does this thing take up protons, or how well does this thing donate protons versus how well this donates protons to form some equilibrium, right? And so when we look at that competing equilibrium, you actually have to do essentially two ice tables that are coupled to each other.
Oh, yeah.
And you go through all of the math and end up getting pH equals pKa1 plus pKa2 divided by 2.
Wouldn't like pKa1 is pretty much like the dominating factor in that? It's
Not actually.
1,000 times bigger.
Not when we're at this point, when we're in between the two, right? So we get to this point now, it's 1,000 times bigger. That means it's dominating on its own. But keep in mind, we've added base, right?
Oh,
We've
yeah.
taken away some protons, right? And so now we're saying, okay, what's the equilibrium after we've taken away some protons? And that's where it's, okay, now the second one can also play a role.
Right. Okay.
And that's where you get, yeah, I was kicking myself once I did this and found out that the simple answer that I was like, that's got to just be like an approximate answer. No, this is actually the answer.
Okay.
You get like an X and a Y and a Z and like like everything cancels. Because if you think about it, you're going to be dealing with a bunch of number of moles. All the number of moles keep canceling out. Yeah, it's weird. This is what you need to know.
Could you talk about the different assumptions that we make at like different points in the titration and buffer regions and stuff?
Yeah. Throughout the entire calculation, we're making one assumption
Water
the whole
is
way.
negligible.
Water's negligible. You notice in all of this, we've never talked about water at all. Even when you get here close to 7, even there close to 7, because of the equilibria of the other things, those kind of dominate over water, right? The fact that we've got weak acid conjugate base, those always play a more important role than the actual water that's there. So water's negligible the whole way through, even close to 7 in these cases. Water's equilibrium is kind of being taken care of with these because we're using H3O plus and OH minus.
But it's like the concentrations, like it's 0.1, but if the concentration of the acid was like
Yes.
10 to the negative 7, then we would probably have to account for water.
Yes, right?
Okay.
So anytime you're dealing with dilute systems, it becomes important.
Okay.
We then have pretty much the first point, all we're doing is exosmol approximation. Throughout the buffer region, we're making 2 approximations. We're making exosmol compared to the dissociation of H2A, and exosmol compared to the amount of HA plus that is there. We're doing 2 exosmol approximations. If we're at one end of the buffer region, one exosmall approximation starts to fail. If we go to the other end of the buffer region, the other exosmall approximation starts to fail. We do the same thing through this area. Right? We say through this area, one approximation fails or the other approximation fails. We also, one exosmall or the other, we're using two exosmall approximations through there. The other thing that we say is this equivalence point and this equivalence point are very different from each other because these two equilibria are really different from each other, right? That's what allows us to say that there's two equilibria. Like there's two things that look like titration curves. Pretty much this whole reaction happens on its own and this whole reaction happens on its own. We know that's not quite true when you're getting to this equivalence point, but it's roughly true. It's an approximation.
Another quick question.
Yeah.
So when we're titrating a weak like a monoproduct weak acid with a strong base, the pH of the equivalence point is usually above 7, right?
Yes.
So
why?
Why is it like in a diproduct when like our pH, like even though it's still a weak acid and we're titrating with a strong base, why does it seem like it's
Good question. Yeah. So when we do a monoproduct, we say equivalence points above 7. When we do a diproduct, we're like, maybe not. In some cases, it will be. In this case, it's not. Now the reason, let's think about the monoproduct case. If we're looking at a monoproduct, again, let's get our curve to kind of think about. We're looking at this point. The only reaction that we're really looking at is HA goes to A minus plus H3O plus. What's the only thing we have left at our equivalence point?
Conjugate base.
Conjugate base A minus.
Yeah.
Can this conjugate base behave like an acid at all? Only behaves like a base. So our pH has to be basic because we essentially only have a base present. Let's look at our first equivalence point for this one. What do we have left?
Something that can act like an acid.
Yeah. So the positioning of this equivalence point depends pretty much on how well does this act like an acid versus how well does it act like a base.
Okay.
Another way to say that is keep in mind this thing's base behavior is just the inverse of this thing's acid behavior. So we can think about it in terms of how does HA behave like an acid versus how well does it behave like a base. You can develop a different equation that kind of bears that out, and you get like a pKa minus a pKb plus a pKw, blah, blah, blah. You get a bunch of stuff that works. It becomes easier mathematically to think about how well does this thing behave like an acid versus how well does this thing behave like an acid. So that's exactly why, because your conjugate base from your reaction can also behave like an acid, so your pH might be, depending on how well it behaves like an acid, might be below 7.
Okay, that makes sense.
Is there a question? Homework 3, problem 15. Anyone want to see homework 3, problem 15? Clear it does. Let's take a look at it. Any other questions on this logic? Okay. Wait, homework 3? Calculate the pH of the solution prepared by adding 200 milliliters of NH3 to 200 milliliters HCl. I think that's homework 5, problem 15. Because that is a weak base, strong acid titration problem.
Homework 315 says calculate the pH of the solution prepared by adding 200 milliliters of 0.5 molar NH3 to 200 milliliters of 0.3 molar HCl.
There's 200 milliliters of 0.5 molar NH3 plus
200 milliliters of 0.3 molar HCl.
Wow. I put that on homework 3?
I think it was probably one of the ones we had to skip over.
Huh. Okay, so we're going to approach this just like we do any other problem. Stoichiometry followed by equilibrium. Now, we're going to do the stoichiometry first, and then we'll see that we can kind of skip the equilibrium. because just looking at this, the reaction that we're looking at, first off, we're going to need the Kb for NH3 in order to do this, which if I remember correctly is like 1.8 times 10 to the minus 5. There's only one Ka and one Kb that I remember. It's the Ka for acetic acid and the Kb for ammonia, because they happen to be the same numbers. Approximately the same. For acetic acid, it's like 1.76. This gives the Ka of, I think, 5.5 times 10 to the minus 10. Do me a favor, calculators, and double check my work
I
there.
have it as 5.6, so yeah, that's right.
Cool. Okay. I think it's like 5.57. I'm rounding too much. I'm rounding too much. Make sure you're using your correct sig figs on the test. Let's see. So let's go ahead and look at the reaction that we're going to have. We're going to have NH3. I don't actually care about the HCl. All I care about is the H plus. And of course, I should treat it as H3O plus. That's going to go to NH4 plus H2O. 200 times 0.5 is 100. And 200 times 0.3, no, that's right, 100. And 200 times 0.3 is 60. Am I okay at math? I'm okay at math. That's in millimoles. That's in millimoles. Start with 0 there. That's my start reaction. Excess. Fortunately, my acid is my limiting reactant, minus 60 plus 60. Math in my head, 40, 0. Oh, no, lies. 40, 0, 60. Notice at this point, what kind of solution do we have? It's a buffer, right? I've got weak acid, I've got conjugate base. I could think of it as I have weak base, I have conjugate acid, and I could go through either equilibrium because I've got both present. It is easier to think of it as weak acid with conjugate base because then it's just pH equals pKa plus log 40 over 60.
So we can only use this equation if it's in the buffer.
Yeah, Henderson-Hasselbalch's in the buffer range.
Is base always above acid for the ratio?
If we're using the Henderson-Hasselbalch, yes, right, is always conjugate base over weak acid. There are different ways you can write this down, and keep in mind this is just a shortcut for the equilibrium. So when I write it as conjugate base over weak acid, that means I have weak acid plus H2O going to conjugate base plus H3O plus products over reactants, right? So as long as I'm doing that equilibrium, products over reactants, we're good. So at this point, we can calculate our pH. We know the pKa. I can't do that one in my head. What's the pKa?
Oh, it's right like that.
9.26.
We have 9.26 plus the log of 40 over 60. That's going to be like 2/3, which is 0.666 log of 0.6. Negative
0.18.
I was going to say 0.2, I swear. So, can't believe I put that on homework 3. I kind of can. 9.26 minus 1.8 is 9.08. Ta-da! again, notice the essence of everything we've done this entire quarter so far. Stoichiometry and equilibrium, just in some different orientation. So as soon as we have some two things interacting with each other, we're probably looking at stoichiometry or equilibrium or both. Usually both, one than the other.
So
Yeah.
we're not gonna have any problems where water's contribution matters, right?
I never said that.
Can we do one of those then?
Okay. Do you have an example you want to look at where the contribution of water is significant?
I don't even think we've come
Yeah,
across
I don't
any.
know.
What's that?
I
Yeah,
don't
have
think
we
we,
done one?
like, I know that you
Yeah.
did that one in lecture, but I don't
Yeah.
think that anything has come up on the homework. So I, like, yeah, did I
So,
recognize
Let's do some logical thinking, right? So, if we've had one example in class and nothing else has really dealt with water being significant, is it likely that I'm going to put a problem like that on the test?
No.
Is
Like,
it
you never
possible? Yes, I never said I wasn't going to, so it's possible. But likeliness, you know,
Is that yes or no?
it's a low probability, right? Yes and no answers, they're so passe. Like chemistry is almost never a yes no
that'd be
answer.
so
It's always a
sad.
how much.
And then add it in now.
I never said no.
So.
Have 127 all over.
So, a typical example where we see water as important is when we're looking at dilute strong acids. Oh yeah, dilute weak acids would be a whole different headache because you'd have competing equilibria then. So let's look at a dilute strong acid. If we've got nitric acid at a concentration of, what's a good low concentration? What's your favorite number?
My favorite number is 7, but like 0.7, I guess.
Yeah. No, we need smaller than 0.7. Okay, so here's a more important question than how do we deal with water contributing. When does water contribute? So someone said times 10 to the minus 5. Let's try this and say, okay, would water contribute at this pH, at this level of concentration? So we're going to be looking at nitric acid. Now, nitric acid just completely disassociates because it's a strong acid into H3O plus NO3 minus, and that's spectator. We don't care about that. So what we're going to do is we're going to look at the equilibrium of water, auto-ionizing. We know that this has a Kw equal to 1 times 10 to the minus 14. We don't care about the waters if we're looking at our equilibrium. We've got 0 hydroxide. We've got 7 times 10 to the minus 5. So if we added plus x, we use the x as small approximation. We say 7 times 10 to the minus 5 and x. If we solve for x,
Why did you put 2 waters?
because it's the water interacting with the water, right? So one's donating a proton and becoming OH, one's accepting a proton and becoming H3O plus.
Okay.
It's the auto-ionization of water.
So we'd have like an insignificant amount of.
Yeah. In this case, it'd be insignificant. I'd have 1 times 10 to the minus 14 divided by 7 times 10 to the minus 5. That's going to be like 1 times 10 to the minus 9 divided by 7. That's going to be like 4 times 10 to the minus 8. Calculators help. I can't actually, don't trust me.
You asked me?
What's x?
One 1.4 times 10 to the negative 10. 1.43.
Yeah, I was off by a factor of 10. I said something times 10 to the minus 9. I was wrong. 1.42 times 10 to the minus 10. Is x significant? No. So in this case, water didn't matter. Let's keep with 7 because it's somebody's favorite number.
How do
And
you-
let's
How
think.
do you know when you have to do the auto ionization of water?
Well,
See if it matters.
you know, so in this situation where we're asking, is water significant? We're always looking at the auto ionization of water. So let's see if we can get to a place where water is significant. Not 10 to the minus 5. Who's got another number they want to try?
9.
Whew, yeah. 10 to the minus 9. We're going to go ahead and do minus x. Oh, sorry, plus x. Plus x. If we made the x a small approximation, let's see if this x a small approximation works. 7 times 10 to the minus 9. That would say, okay, like making this x a small approximation essentially says water doesn't matter, right? The amount that water's disassociating is insignificant to the amount of H3O plus I already had. If we solve for x in this case, what value do we get? Is that okay?
Might be 7.
Oh, can I see your calculator for a second?
Sure.
Here, watch this. You're getting a second, sorry. It is 6. So we look at this and say, great, that's our x value. Are there any problems with that x value? What's wrong with that x value?
It's bigger than the original concentration.
It's bigger than the original concentration. The x is small approximation fails here by a factor of 10,000. The x is small approximation is terrible here. That's a wrong answer. X is small fails. This means that water's contribution is significant. It also means that when we want to calculate this, we have to do 1 times 10 to the minus 14 equals 7 times 10 to the minus 9 plus x times x. We're going to get x squared minus 7 times 10 to the minus 9x. Nope, plus that. Minus 1 times 10 to the minus 14 equals 0. And then we can, you know, x equals negative b plus or minus square root b squared on b squared minus, oh, I forgot. Minus 4ac all over 2a. And then we can solve it. Again, I would not ask you to solve the quadratic. I would want you to get to here and say, oh, the x is small approximation completely fails. That means water is significant. And I can show you why I know that to be true, because if I take this number, I compare it to my original concentration, clearly x is bigger than my original concentration. There's a mistake. So in order to actually do these problems, we'd have to solve the quadratic to get what the actual pH would end up being.
So if you were to solve it and then realize that water's contribution is important and it was asking you what the pH is at the end, like, would you add up the original value from the HNO3 dissociating and then?
You would add the original plus whatever your x was.
Okay, and it would be the x from the quadratic.
Exactly.
Okay.
So we're not gonna.
I would not ask you to solve the quadratic. I would ask you to, you know, show it from here.
Can you quickly go over one last thing?
Yeah. One last thing.
The pH, or not the pH, the buffer capacities, like there was a problem on, I think, homework 4, and it was comparing, like, they each have like 1 molar of acid base. Yeah, like
Which
how do
thing
you
has
know?
the bigger buffer capacity?
Yeah.
So when we are doing, and that was qualitative, not quantitative, right? It wasn't asking you to actually calculate. It was just like compare.
It was saying calculate and then compare, like how well it works, but I know that there's like gotta be a way to compare it without calculating.
There's a way to compare without calculating. Yeah. So remember, buffer capacity depends on 3 things. Remember, buffer capacity, again, if we're thinking about a titration curve, the capacity is just the x-axis, right? It's just a volume. That means it's going to be completely dominated by the stoichiometry. So when we look at this, we know that it's going to depend on the molarity of buffer. It's going to depend on the volume of buffer. Right? How many moles of buffer are there to react? That's going to be one. That's going to be the first thing that matters. If I'm looking at a teacup of buffer versus like a gallon of buffer, like a 55-gallon drum of buffer, clearly one's going to take more titrant to get through the buffer range. The more volume, the bigger the capacity. Also, how much buffer material is actually there. Like if you've got a teacup, but it's like 6 molar, and you've got your 55-gallon drum, but it's like 0.001 molar, that's also going to have an effect. How much material, not just the volume, but the amount of material inside that volume, right? It's the number of moles. Then it's also going to matter how strong the stuff you're adding is. The molarity of the titrant. If you're adding 0.01 molar base to something, it's going to take that's going to make your volume to get through the buffer capacity, the buffer range, really long. If you're adding 10 molar, kind of unrealistic, let's say 6 molar, then that's going to abbreviate how much volume it takes. So really, we just want to compare these three things. That's a lot of what the buffer slab was actually doing was, what happens if we dilute it? What happens if we take different volumes? We didn't really mess with this last one. Although some of you did accidentally because you took the wrong base. But
So, like, if you were comparing, if it gives you, like, you have 3, it was saying, like, you have 3 molar of the acid and then, like, 1 molar of the base, but there was another one, like, I don't have the problem. Yeah, it was.
let's see if we can figure out what problem this is real quick. This is the last thing we're going to do because I need to eat before 6 hours of class. That's okay.
Oh my gosh. Was it, maybe it was.
Okay. I'll answer
It was 13.
the live question and this question. So let's take a look at number
Okay, so yeah, it was
13.
problem 13, yeah.
Problem 13 says buffer A is made from that, buffer B is made from that, buffer C is made from that. So 1 liter for each. So, this is interesting. Well, so just on a quick thing, so finding the pH of each buffer is just Henderson-Hasselbalch.
Mm-hmm.
We're looking at homework 4, problem 14. Let's see if I can do this. Does this work? That doesn't really work. No, it's not actually reversed. It's just YouTube messes with us. Part A is just Henderson-Hasselbalch. Part B is modifying it and figuring out what the smallest percent change is. And then part C is adding more and seeing which the percent change is. And then doing it in reverse. So the main thing we want to see here, so this is actually not just asking us for a qualitative comparison.
Yeah.
It's actually asking us to do a bunch of calculations to see how much it actually does change. In each of these cases, I think we stay in the buffer range for each of them, and it never asks for like which has the best capacity. But if we wanted to say which has the best capacity, buffer A is made from, if we look at total concentrations, buffer A has a total concentration of 2 molar. Buffer B has a total concentration of 4 molar, and buffer C has a total concentration of 4 molar. So A is the worst.
Mm-hmm.
B and C are both about the same.
Okay.
But then the rest is actually calculations like the buffer calculations
Okay.
from the lab. The last question I'm going to answer is, how does a buffer work and what are the 2 ways to make a buffer? So a buffer works, the 2 ways, and the problem we were just looking at, that was homework 4, problem 13, is getting at how a buffer works and is one of the ways to make a buffer. So let's do it in the context of that problem. That was NH3 and NH4 for all of them, right?
Yeah.
Let's do it for the acidic case. So we're going to do NH4 plus goes to NH3 plus H3O plus. A buffer is whenever we have, like, let's say 0.1 and 0.3. A buffer is whenever we have a weak acid and a conjugate base both present. So that way, whichever way we will look at the reaction, if you add base, a weak acid, right? And so there's a reaction. So if we just put it in water, the base is just hydroxide in water, and it's just your pH shoots up. But when you add it to a buffer, it reacts. And that's going to make it so the hydroxide addition has a less significant impact on the pH. If you add acid, it reacts with the weak base. You can call it a conjugate base, but it's going to react with this. Right, and again, we get the same thing. Instead of just it being like H3O plus, there's just more H3O plus in solution. First, we have to react away this material before the addition of acid becomes significant. So essentially a buffer, the functionality of a buffer is much more important than like the capacity, but this is how a buffer kind of resists change. The thing that makes buffers more useful is the fact that this equilibrium will have a particular pH, and we can use our different buffer systems to pick which pH it will be stable, which pH will stabilize. Now, how do we make buffers, right? So a buffer is anytime I get weak acid and conjugate base or weak base conjugate acid. So one way to make a buffer, dump in weak acid and dump in conjugate base, right? You get NH3, you get ammonia, you dump in ammonium chloride, that makes a buffer. So you can just add weak acid and conjugate base into one solution. That would be, instead of doing a titration, that would just be immediately you're at the right spot. Which is in industry how you usually do it, right? If you need 250 milliliters of a buffer, you don't go, oh, let me get one material and then titrate to the right spot. You just get your two materials and you dump in the right ratios and you're done. What we've been doing in class, because we wanted to have like a more academic understanding of how this works, is we've been mostly doing it the second way, which is see ya. We've been titrating our weak acid to create some amount of conjugate base. That's the second way that you can make a buffer, is you can just do it through titration. And that's how we've been doing it in lab. We've always been doing it via titration. Okay? Okay, I have to eat before I have 6 hours of class. I've got 6 hours of class tonight. 3-hour lab, 3 hours studio.
While I was gone, did you guys talk about like midterm questions or homework
No, not really.
questions?
See ya.
Homework questions?
I hope that was okay for everyone watching. See you tomorrow.
Signing off.